a 3+ hemoglobin or a met hemoglobin or a HbM. So when HbM is there, the hemoglobin cannot transport oxygen. So when there is no oxygenated blood, the red color of the blood disappears and is replaced by a blue colored blood. So that condition is called as cyanosis. That condition is called as cyanosis. So this is the basic backdrop of hemoglobin entity. So now let us move into the synthesis part. How is hemoglobin synthesized? So the synthesis of hemoglobin is a separate topic in itself. Synthesis of hemoglobin is a separate topic in itself. What happens here is basically the hemoglobin synthesis at the time of consumption, sorry, not consumption, at the time of conceiving starts from the yolk sac. Okay, so the yolk sac is the first source of synthesis of hemoglobin. Then as the baby grows, the yolk sac is replaced by the fetal liver as the primary source of hemoglobin, that is through the organogestational period of 18 to 55 days. Okay, number 3, as the baby nears term, as the baby is going to be born, the fetal liver gives rise to the bone marrow cells or the osteocytes. Then these are the primary stores of hemoglobin synthesis, so that this is going to retain as the primary source of hemoglobin when the baby is born and it continues into the adult life. Now I told you there are 3 types of hemoglobin. The hemoglobin A constitutes 95 to 98% of the basic adult hemoglobin. The fetal hemoglobin contributes to 1.5 to 1% and the HbA2 contributes to 2 to 3%. Contributes to 2 to 3%. So hemoglobin A is 95 to 98% and HbF is 0.5 to 1% and HbA2 is 2 to 3%. So the other question which they might ask you is, how does the hemoglobin run when it comes to the electrophoresis? So this is called as the hemoglobin electrophoresis. Whenever you tell the name electrophoresis, there's gonna be a minus end and there's gonna be a plus end. Basically, this is something similar to a battery. In a battery, you have a minus end and you also have a plus end. So electric field is created only when there are 2 poles, a negative pole and a positive pole. So this is called as an electric dipole. So there is a charge movement which is happening between the 2 charges. That means that the molecules or the charged molecules are going to move from the negative end to the positive end. Always the setup is like the molecules move from the negative end to the positive end. So the molecules which are having more negative charge are gonna be displaced faster towards the positive electrode. So that is basically how the things are here. So let us assume this is the point of application. I'm going to write this as POA, point of application. So when the point of application, you apply the sample here. Let us assume you apply the sample here. So the migration is going to be that whichever molecule is having a greater negative charge is going to migrate the farthest. So that particular molecule is called as HbA. That particular molecule is called as HbA. Then you have next HbF, and towards the point of application it is HbA2. Towards the point of application it is HbA2. So more the negative charge, the farthest the movement. So less than the negative charge, it stays close to the point of application. So this is how the hemoglobin electrophoresis runs. There is another fraction which is even more powerful than the HbA. It can run even farther than the HbA. This is called as the Bart's hemoglobin. I will come to Bart's hemoglobin towards the end of the session. This is called as Bart's hemoglobin. So whatever I have told so far is everything is an MCQs. Whichever have been asked so far in MCQs, that only I have been telling this. And basically this is the fact which you must write when you are writing an essay question on hemoglobin. This is the basic introduction you must write. See, whenever you write an essay question, you must start with the molecule as such, the basic chemistry as such, and then you progress towards the characteristics, and then you round it off with applied aspects are the clinical disorders which are associated with that particular chemistry entity which you are talking about. Okay, so let us come here. Basically, there are striking similarities between the hemoglobin molecule and another protein molecule which is present in the plants. Basically, look here, the iron molecule is the center of the human oxygen transport protein, but in the plants there is a magnesium molecule which is bound to 4 different proteins, and this particular protein is called as chlorophyll. So in the plants, the chlorophyll, whatever the chlorophyll does for the plants is exactly done by the hemoglobin in the humans. So basically hemoglobin is an similar protein to chlorophyll. So what exactly is going on? If you see here, I'm going to use a pointer here. So look at my pointer carefully. So if you see the green color moiety, this is the heme molecule. Here is another heme molecule. Here is another heme molecule, and this is here is another heme molecule. And what is this coiled structure? The coiled structure is basically nothing but 2 alpha chains. This is alpha 1 and alpha 2, and this is beta 1 and beta 2. So what exactly is happening in the hemoglobin is, you understand like this structure. You need to look at this structure. The iron moiety is at the center. And what is the iron moiety charge? They have not mentioned the charge, but the charge is Fe2 plus. Okay, so the iron moiety is exactly at the center, and the iron moiety is attached to 4 rings. These are called as the 4 pyrrole rings. So I'm going to write this as like this. There is iron in Fe2 plus state in the center, and this iron is linked to 4 pyrrole rings. So that's why it's called as a tetrapyrrole. Tetrapyrrole. So this iron is, you can see the nitrogen here, right? 1, 2, 3, 4. So each nitrogen belongs to a pyrrole ring. So the pyrrole ring is a specific ring which is having an aromatic ring-like structure. So this pyrrole ring is attached to the ferrous molecule. So ferrous iron, and these are basically 4 linkages. Iron is connected to 4 pyrrole rings. So that is the tetrapyrrole. Does this iron stop with this? No, the iron does not stop with this. So what happens is, this iron is also linked to 2 other people. One is, this iron is linked to the globin chain. So they're either alpha 1 or alpha 2 or beta 1 or beta 2, any other moiety. Okay, and then the last linkage is with oxygen. So basically I told you, iron molecule, hemoglobin contains oxygen. So hemoglobin has to bind to oxygen. So basically I told you, a hemoglobin molecule can have binding to 4 iron molecules, 4 oxygen molecules. So if you look at here, each heme molecule will be bound to 1 oxygen. This 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 will be bound to 1 oxygen. So one heme binds to 1 oxygen. Totally there are 4 heme molecules. So 4 oxygen molecules can be carried by the hemoglobin. So here, if you want to see, I am speaking to you about heme structure. I'm not speaking about the globin chains. The globin, you just keep it separately, alpha 1, alpha 2, beta 1, beta 2. What I'm trying to speak to you about is the heme structure. The entire heme structure is basically an iron containing metalloporphyrin. Iron is in the center, Fe2 plus charge, linked to 4 pyrrole rings called as a tetrapyrrole. Other than the 4 pyrrole rings, it is also linked to the globin moiety, and it is also linked to the oxygen. So totally there are 6 linkages. If you want to write that, you can write that as totally there are 6 linkages. Totally there are 6 linkages. Okay, good. So now what other thing happens here? So if you want to see here, there is another thing called as the histidine moieties. So another favorite topics when it comes to MCQs. What are the histidine moieties? There are 2 histidine moieties. One is called as the proximal histidine. The other is called as distal histidine. So histidine moieties are heme. Histidine moieties of heme. What? Histidine moieties of what? Histidine moieties of heme. So basically, there are two histidine moieties. What is the function of these histidine moieties? The proximal histidine is otherwise called as histidine F8. The histidine molecule, which is in the distal region, is called as histidine E7. Histidine E7. So histidine F8 stabilizes the structure of heme. Stabilizes the structure of heme. And the histidine E7 facilitates oxygen binding. Facilitates oxygen binding. So there are two E moieties. Histidine at the proximal. The histidine which is closer to the heme is called as the proximal histidine. The histidine which is farther away from the heme molecule is called as the distal histidine. The proximal histidine stabilizes the structure of the heme molecule, whereas the distal histidine facilitates O2 binding. So basically, the histidine is an amino acid which is present in the hemoglobin. So the last point is histidine is an amino acid which is present in the hemoglobin. And this histidine has a pKa and a dissociation constant, which is closer to the body pH. So whenever an amino acid has a dissociation constant pKa, which is close to the body, as much close the pKa is to the pH, that much better buffer. That molecule acts as a buffer. So what is meant by buffer? Buffer is a substance which resists changes in the pH. So basically, we need to maintain the body pH at 7.35 to 7.39. Okay. So you have somebody asked me a question. Let me see that. 1 minute. So some network issue. Can you brush up? Okay. Okay. I will try summarize. Okay. Fine. So whenever a pKa histidine has a pKa molecule of pKa of closer to body pH, any amino acid for that instance, as much close the pKa is to the pH, then that much better the buffer is. So the buffer resists changes in the pH. Our body tries to maintain the pH at 7.35 to 7.39. So basically, this 7.35 to 7.39 is the zone at which the body is comfortable. So the body has a lot of buffers, intracellular buffers, extracellular buffers, protein buffers. One of the very important buffer is hemoglobin. And the reason why the hemoglobin is a good buffer is because this hemoglobin has a histidine moiety. That is exactly the reason why the hemoglobin is a very good buffer. Okay. Okay, just give me a minute. 1 minute, I just be back. Okay, now. So someone is asking for a repeat of so far. So far, what I have told, I will just summarize in 1 minute. So hemoglobin is a molecule which has heme and globin. Globin has two alpha and two beta subchains. Heme is actually a separate entity. Okay, so heme is an iron containing porphyrin or a metalloporphyrin. So hemoglobin is basically a quaternary structure, highest order of the structure, and hemoglobin has a function to transport oxygen. So how much molecules of oxygen? 4 molecules of oxygen. How much iron does it contain? 3 to 4 mg of iron. And Hemoglobin can transport only oxygen when the heme contains iron in the ferrous state. So somebody has to maintain the iron in the ferrous state. If it's in the ferric state, then it cannot transport oxygen. Okay, so and then I told you about the different types of hemoglobin. The different types of hemoglobin, major types of hemoglobin are adult hemoglobin, 95 to 98% of our body, 90 adult hemoglobin, and then the HbA2 variant is about 2 to 3%. And HbF is 0.5 to 1%. And when you take an electrophoresis and run, the adult hemoglobin has the maximum negative charge, so it runs the farthest, whereas the A2 fraction has the minimum negative charge. It stays close to the point of application. So how is hemoglobin synthesized? Hemoglobin is synthesized basically during birth, during conceiving. At the time of conceiving, it's from the yolk sac, and as the baby matures, it shifts towards fetal liver, and at the time of birth, around 36 weeks, the primary focus of synthesis of hemoglobin is from the bone marrow cells. Okay, so that was the first page I have taught you. Is my screen visible? Share. Okay. Okay. So then I went to teach about the heme molecule. Heme molecule has a specific linkages. The specific linkages, basically 6 linkages are there. The heme is attached to 4 pyrrole rings, tetrapyrrole, and then it's also attached to the globin moiety. It is also attached to the oxygen molecule. And who is helping the heme to do all these things? There are 2 histidines. One histidine is closer to the heme, which is called as proximal histidine, which stabilizes the structure of heme, and there is a distal histidine which facilitates O2 binding. Okay, now about the conformational structure of hemoglobin. Hemoglobin is basically existing in heme is basically existing in 2 states. One state in which the oxygen is bound to the hemoglobin, and the other state, the oxygen is not bound to the hemoglobin. The state in which there is no oxygen is called as the T state or the 10th state. So 10th state, no O2 bound. So point number 1, it is very tense, is no O2 bound. Whereas the R state or the relaxed state, oxygen has bound. So what basically happens when the oxygen binds to the hemoglobin is you think like this. Basically, this is the hemoglobin molecule, and I'm gonna write the oxygen like this. So oxygen is bound to the heme. So when one oxygen binds, what will happen is that between these two heme molecules, there is something called as a methanol bridges. These are called as methanol bridges. So in some books, it's also called as a salt bridges. So the heme is basically in a very tight bound form. When oxygen binds, these methanol bridges break. So it cuts loose. So it's like this, and then it cuts loose. This linkage is gone when the O2 binds. So what will happen is this O2, when one molecule of O2 has bound, it will call the other molecule of O2 to bind. So it will call another fellow, come, you also bind. So the second linkage will go. Then these 2 fellows will call the another one oxygen molecule. This will also go. Then this finally will call another one oxygen molecule. This will also go. So totally 4 oxygen molecules has to bind, and this is facilitated by the molecule of single oxygen molecule. This fellow will call the second one. The second one will call the third one. The third one will call the fourth one. This phenomenon is called as cooperative binding. This phenomenon is called as cooperative binding. And with every single oxygen which is bound to the heme molecule, the salt bridges get ruptured. And when the salt bridges get ruptured, slowly the transition of hemoglobin happens from the tense state to the relaxed state. So from the T state to the R state. So basically T state is a state in which there is no oxygen bound to hemoglobin, whereas the R state is a state in which the oxygen is bound. Whenever the oxygen is bound, the salt bridges are ruptured. When the salt bridges are ruptured, it leads to further binding of another one oxygen molecule. So 1 leads to 2, 2 leads to 3, 3 leads to 4. This phenomenon is called as cooperative binding. Okay, understood. So now we will come to the next classification. So I'm going to teach you again the same molecule. So I told you there are 4 rings: pyrrole ring 1, pyrrole ring 2, pyrrole ring 3, pyrrole ring 4. But what I didn't teach you is the pyrroles have side chains. The pyrroles have side chains. So what are the 4 basic side chains? Methyl group, vinyl group, acetyl group, and propionyl group. Methyl, vinyl, acetyl, and propionyl. So basically nobody wants to get into the details of all these things, but then the people at AIIMS, the people at central institutes are very obsessed about the arrangement, configurational arrangement of side chains, configurational arrangement of side chains. Okay, so what happens here is, again, I'm going to write the same molecule structure. Okay, so the side chains can be arranged symmetrically like this. So M, V, M, V, M, P, M, P. So there is some kind of an order here: methyl followed by vinyl, methyl followed by vinyl, methyl followed by propionyl, methyl followed by propionyl. If it is arranged like this, then it is called as class 1 porphyrinogen. It is called as class 1. But there are some times when the arrangement will be haywire. Okay, now look at like this: methyl vinyl, methyl vinyl, propionyl methyl, methyl propionyl. So if you see here, the order is skewed. So basically it's an asymmetrical arrangement of side chains. When there is an asymmetrical arrangement of side chains, then it is called as a class 3 porphyrinogen. This class 3 porphyrinogen is a human porphyrinogen. In humans, it is basically class 3. In humans, it is basically class 3. So now you get a question, sir, what is this? So I told you about something called as porphyrinogen. So anything which contains the tetrapyrrole rings is called as porphyrinogen. But the problem here is the porphyrinogens are colorless. When the porphyrinogens are oxidized, exposed to oxygen, then they become porphyrins. Then they become porphyrins. These porphyrins are colored compounds. Porphyrins are colored compounds. So the same goes for something called as urobilinogen. Urobilinogen is a molecule, precursor molecule, colorless. Okay, but then it's oxidized. When it is exposed to air, it converts itself to urobilin, which is yellow in color. That's why the urine is yellow in color. Stercobilinogen, colorless, but when it's exposed to air, it's converted to stercobilin, which is brown in color. So that's why the stools are brown in color. So there is a test which detects all these things. So this test is called as Watson-Schwarz test or Ehrlich's test. It's basically a test done to diagnose whether there is a presence of porphobilinogen or urobilinogen in the blood or urine. So you must know this because they will ask you in MCQs. Which test is used to assess porphobilinogen or urobilinogen? It's Watson-Schwarz or Ehrlich's test. Okay, so this has to be remembered: porphyrinogen, porphobilinogen, urobilinogen. Gen, anything with gen is colorless. Okay, anything with urobilin, stercobilin, porphyrin, these are colored compounds. Heme is a metalloporphyrin, that is why it is colored red color, and that is why the blood is also red color because of the oxygen attached to the heme. Okay, so you must be able to understand this particular concept. Please remember again, porphobilinogen, urobilinogen, stercobilinogen, colorless. When it's oxidized to air, then it becomes colored compounds. If you want to know this very much, then you see the veins in your hand are basically blue in color. They do not contain oxygen. They are having deoxygenated blood. So, but when you cut the veins, is the blood coming out in blue color? No, the blood comes out in red color. That is because when the vein is cut, the blood is immediately exposed to an air which is containing 78% nitrogen and 21% oxygen. 21% oxygen is so huge that within fractions and fractions of milliseconds, the blood changes its color from blue to red, which is not even able to be captured by your eyes. So that is basically oxygen that converts the deoxygenated blood into oxygenated blood, and that's why you see the blood as red color even when you cut the veins. Normally arterial blood will sprout, it will come as red color, but when the venous blood should come as blue color, but it is coming as red color. That is because of the atmospheric oxidation. Okay, so that's fine. So let us now go into the heme synthesis. So the first point is heme is a molecule which is synthesized from glycine plus succinyl-CoA. So glycine is the simplest amino acid. So basically, that's why I told you heme comes under protein, because it is synthesized from an amino acid, glycine plus succinyl-CoA. The point number 2 is part of the reaction happens in mitochondria, part happens in the cytoplasm. Part happens in the cytoplasm. Okay, so to come to the next page. So this is basically the pathway of heme synthesis. So look at here. Glycine plus succinyl, the reaction kicks off in mitochondria. The glycine plus succinyl-CoA is acted by an enzyme called as ALA synthase. ALA synthase. The difference between synthase and synthetase is synthase does not use ATP. Synthetase means uses ATP. So synthesis using ATP, synthetase. Synthesize without ATP, synthase. The cofactor is B6. So you must understand this. Whenever pyridoxine is not there, then heme is not synthesized, hemoglobin is not there, can lead to anemia. So basically, vitamin B6 deficiency also can lead to anemia. So that is exactly the point you must know. So the first step is glycine plus succinyl-CoA gives rise to delta amino levulinic acid. This is called as amino levulinic acid. And that component is migrating from the mitochondria to the cytoplasm. So there are molecules of delta amino levulinic acid, otherwise called as ALA, which is coming to the cytoplasm. And once it enters into the cytoplasm, there is a water molecule which is removed by an enzyme called as dehydratase, ALA dehydratase. So this ALA is now converted into a component called as porphobilinogen. It is converted into a compound called as porphobilinogen. Now I want you to make a change over here. So I want you to cut off this thing. I want you to cut off this enzyme. I want to write a new enzyme here. It is called as PBG deaminase. It is called as PBG deaminase. So what we are basically going to do is we are going to remove 4 molecules of ammonia. That is the reason why I told you to write PBG deaminase. So you will remember it better. PBG deaminase. So what will happen is when you remove 4 molecules of ammonia from porphobilinogen, this porphobilinogen is converted into a component called as hydroxymethylbilane. It's called as HMB. It's not the HMG which comes in the lipid metabolism. Okay, that's hydroxymethyl glutarate. Okay, this is hydroxymethylbilane. Okay. So this hydroxymethylbilane has 2 fates. It can give rise to class 1 compounds. spontaneously, or it can be acted by an enzyme called as uroporphyrinogen 3 co-synthase to give rise to 3 compounds. Uroporphyrinogen 3, class 3 compounds. I basically told you hemoglobin or heme is a class 3 moiety. So we will discard the type 1 molecule. We will only proceed with the type 3 molecule. So first step is ALA synthase forms a delta aminolavulinic acid. It jumps from the mitochondria to the cytoplasm. Delta aminolavulinic acid, one water molecule is removed, knocked off by ALA dehydratase, becomes parphylbilinogen. From parphylbilinogen, ammonia is removed, PPG deaminase, it gets converted to hydroxymethylbilane. Hydroxymethylbilane can spontaneously be converted to class 1 or it can be converted to class 3 uroporphyrinogen. So this uroporphyrinogen can be excreted via urine because it's a water-soluble compound. But now this uroporphyrinogen loses a molecule of carbon dioxide. That's the enzyme will be called as uroporphyrinogen decarboxylase because it loses a carbon dioxide and it is converted to coproporphyrinogen. This is a feces molecule. So this is urine. This is feces. Copro means feces. Coproporphyrinogen. 3. Of course, 3, no? Because it's all class 3. This coproporphyrinogen 3 then jumps from the cytoplasm to the mitochondria. So the pathway started in the mitochondria, came to the cytoplasm. From the cytoplasm, it enters back into the mitochondria again. And it undergoes oxidation by a coproporphyrinogen oxidase to give rise to protoporphyrinogen 3. To give rise to protoporphyrinogen 3. Which undergoes again oxidation. You know, whenever porphyrinogens are oxidized, they become porphyrins. So this is a porphyrin. Now it becomes a colored compound. Now it becomes a colored compound, protoporphyrin 3. So uroporphyrinogen decarboxylase gives rise to protoporphyrinogen. So coproporphyrinogen. Coproporphyrinogen enters into mitochondria, gets oxidized to protoporphyrinogen. Protoporphyrinogen, when it's oxidized, it converts into protoporphyrin. Why the oxidation is happening in the mitochondria? Because oxygen is available in the mitochondria for electron transport chain. The enzymes which can process oxygen are in the mitochondria. That is why the pathway very cleverly jumps from the cytoplasm to the mitochondria at these steps where the oxidations are involved. Finally, we have a porphyrin ring, but what we lack, we don't have an iron molecule, but iron molecule is there only, then it becomes a metalloporphyrin. So we need to put up the iron molecule into the porphyrin ring. That is done by an enzyme called as ferrochelatase. Chelatase means join. So somebody who joins the iron into porphyrin ring is called as ferrochelatase, and final product is heme. So basically, heme is a protoporphyrin with the iron molecule joined to the center of the protoporphyrin by the enzyme ferrochelatase. So if you see carefully, this is a very, very simple pathway, but then in the NEET exam, two questions have been asked from this single page of the workbook. The first question, which is the rate limiting step of this pathway? Last class itself, I told you the difference between rate limiting and the regulatory steps. The rate limiting step is ALA synthase. Number 2, which are the 2 enzymes which are inhibited by lead inhibition? So that was the MCQ asked in the NEET exam. ALA dehydratase and ferrochelatase. When 2 options are, both the 2 are there, then you will go for ALA dehydratase because it's a proximal enzyme in the initial part of the pathway. Okay. Now, supposedly, whenever you learn a pathway, you must learn about the regulation of the pathway. So here, 2 enzymes you must write. So you must learn about who are the fellows who increase the pathway, who are the fellows who decrease the pathway. Okay. So who are the fellows who increase hemoglobin synthesis? Steroids. And barbiturates, drugs like barbiturates. Now, who are the ones who decrease the pathway? So all this is by acting on the ALA synthase enzyme. All this by acting on the ALA synthase. So glucose, heme is by negative feedback mechanism. So the formed heme itself goes back and tells, please don't produce me more. I am already enough. And the heme degradation product called as hematine. So more heme means more hematine. Hematine will also inhibit ALA synthase. ALA synthase. Okay, done. Now you must understand what will happen if some of the enzymes in heme metabolism is absent or defective. It will lead to accumulation of porphyrins. It will lead to accumulation of porphyrins, and this will lead to a disease called as porphyrias. This will lead to a disease called as porphyrias, which is very, very important. Porphyrias. So the basic classification of porphyrias is two. Hepatic porphyrias, the ones which affect the liver, and then erythropoietic porphyrias. Erythropoietic porphyrias. So porphyria is basically accumulation of porphobilinogens or porphyrinogens, and all the porphyrinogens have a typical tendency to cause photosensitive lesions. So all the porphyrias have photosensitivity. That is because these patients are scared of light, because the porphyrins absorb light, they cause irritation, they cause itching, they cause painful sensation. So they all present with photosensitive lesions. So many people do not take porphyrias well. So they do not assimilate porphyrias well, but I will give you a mnemonic. If you remember the mnemonic, then you will do well. Okay, so you know the pathways. I'm going to revise the pathway again. First step, ALA synthase, aminolevulinic acid, then knock off a water molecule, ALA dehydratase. Then you take a amine molecule, that is why deaminase, PBG deaminase, porphobilinogen deaminase. Then hydroxymethylbilin has two phases, class 1, class 3. We'll stick with class 3. Uroporphinogen co-synthase 3, that is important here. They have missed the 3. So uroporphinogen 3 you will get. Fine. Then it will be decarboxylated. One carbon dioxide is knocked off. Then you will get coproporphinogen, which will jump into the mitochondria to get oxidized. And finally, protoporphinogen again oxidized to protoporphyrin, and then you put the iron molecule inside. So these are the sequence. Now the enzyme here, the mnemonic here is Assistant Commissioner Police has various enemies. So you will write underline the first 6 entities, ACPHVE. So our porphyrias start from the accumulation of porphyrinogens. So which is the first porphyrinogen? The first porphyrinogen is porphobilinogen. Porphobilinogen. So what is the enzyme that must be defective for accumulation of porphobilinogen? It should be PBGDMS. If this enzyme is cut off, then porphobilinogen accumulates. This enzyme is cut off, then porphobilinogen accumulates. So basically, I told you Assistant Commissioner of Police has various enemies. So Assistant Commissioner, the A is acute intermittent porphyria. So porphobilinogen deaminase deficiency leads to Assistant A, acute intermittent porphyria. So now we will go one by one. The next one, Commissioner of Police, Assistant Commissioner, that is uroporphinogen co-synthase deficiency, congenital erythropoietic porphyria. Police, porphyria cutanea tarda, enzyme deficiency, decarboxylase. Has H, right? Hereditary coproporphyria, enzyme is coproporphinogen oxidase. variegate porphyria, variegate protoporphinogen oxidase. Finally, enemies, erythropoietic porphyria, ferrochelatase. Erythropoietic porphyria, ferrochelatase. So that is the mnemonic. Austin Commission of Police has various enemies. So now they're not going to ask you, very rarely they will ask you which enzyme is connected to where. But what they are going to ask you is this: which is the most common porphyria of all? MCQ number 1. That is porphyria cutanea tarda. That is the most common porphyria of all. Number 2. All the porphyrias are hepatic porphyrias except only one. So only erythroid porphyria, which is the one? Congenital erythropoietic porphyria. Deficiency of uroporphinogen decarboxylase. Correct, no? See, I told you. Uroporphinogen co-synthase. Sorry, uroporphinogen co-synthase 3. Number 3. Only porphyria. All porphyrias have photosensitive lesions, I told you. There is only one porphyria without photosensitivity. Which is that porphyria? Acute intermittent. Acute intermittent. The last MCQ, most severe porphyria. That is also again acute intermittent. So then if again and again people are telling acute intermittent, then you must know what are the symptoms of acute intermittent porphyria. Acute intermittent porphyria is increased PBG, correct? Parfobilinogen, point number 1. And this parfobilinogen can cause abdominal pain, severe abdominal pain, and neuropsychiatric manifestations. Neuropsychiatric manifestations. So basically, this is a patient who complains of severe abdominal pain. They will take all the investigations, but everything will come out normal. They never think about the porphyria spectrum. So what happens is this fellow will even undergo explorative laparotomies. Nothing is found in the abdomen. No problem. Everything is fine. The problem is not in the abdomen. The problem is accumulation of parfobilinogens, which is causing the abdominal pain. And this parfobilinogen can irritate the myelin sheath. That is why it's causing the neuropsychiatric. It keeps on ranting. And if this parfobilinogen is present in the urine, then the urine will be tested by using a test called as Ehrlich or Watson-Schwarz. So I told you, but this is a very light sensitive molecule. So whenever you send a test for porphyrias, you must wrap the bottle with a black color sellotape paper, and then you have to send it to the lab, because if you send it open, the bottle will be exposed to light and we might get breaking down of the parfobilinogen. So that is a Watson-Schwarz test or Ehrlich test. Okay. Do I have some questions? Okay. Again, same question is coming again and again. I have marked it as answered. Okay, no problem. Fine. So let's move on. So with this, we are completing the heme porphyrias, heme synthesis all the time, completing. Okay. Now, I'm gonna teach about what's going to happen when the RBCs are broken down. So basically, understand this concept. We have the RBCs. We have the RBCs. The RBCs are loaded with hemoglobin. The hemoglobin is composed of The hemoglobin is composed of heme and globin. Fine, everything is good so far. So what will happen when the RBCs are broken down? When the RBCs are broken down, this hemoglobin will be released. Hemoglobin will be released. And if hemoglobin is released, then it will start breaking down into heme and globin. But the body is very, very sensitive. The body does not believe or does not have like to lose the components of the important protein hemoglobin. So what it has is it has something called as sequestration mechanisms. Sequestration mechanisms. So it sends across two proteins. One protein to recover all the heme which is lost. That protein is called as hemopexin. So hemopexin binds to the heme, and sequester it. What about the globin part? The globin part is sequestered by heptaglobin. Heptaglobin sequesters globin. So now the question here is, what will happen to the heptaglobin levels in hemolytic anemia? When there is hemolytic anemia, the hemoglobin is lost in massive numbers. So the globin moiety is lost in massive numbers. It can go and clog the renal vessels. So what the body does is it sends all its heptaglobin to bind to the globin chains and sequester the globin chain. So basically the heptaglobin in the body, it's used up. So the heptaglobin levels are decreased in hemolytic anemia. That's an MCQ. Heptaglobin levels are decreased because of the consumption. Something like your disseminated intravascular coagulopathy. It's also called as consumption coagulopathy, right? DIC. So like that, the heptaglobin is used up by the body to sequester the hemoglobin in the case of hemolytic anemia. So that is exactly the reason why we got knocked off. All the heptaglobin levels are reduced. So what happens to the heme? So globin part I have told you. What happens to the heme? The heme is acted by an enzyme called as heme oxygenase, which converts it into a molecule called as biliverdin. Which converts it into a molecule called as biliverdin. This biliverdin is acted upon by an enzyme called as biliverdin reductase to get converted into a compound called as bilirubin. But the problem here is this bilirubin is water insoluble. So we need to excrete everything. This process by which the molecules are trying to be converted from a non-toxic component to a toxic component, or from a water insoluble component to a water soluble. The main idea behind converting the water insoluble component into a water soluble component is you need to excrete something via urine, then it has to be a water soluble component. So water soluble component, what is a water soluble component? Some moiety is there which makes the molecule as a water soluble component. So the bilirubin, which is broken down from the heme, is coming out as a water insoluble molecule, but we need to excrete that. So if we don't excrete that, the bilirubin is going to be loaded up in the body. It is going to cause a disease called as jaundice. We don't want that to happen. So what happens is we try and convert this water insoluble bilirubin into a water soluble bilirubin. So how is that done? It is done with the help of a process called as conjugation. It is done by a process called as conjugation. So this bilirubin is conjugated with a molecule called as glucuronic acid. It's conjugated with a molecule called as glucuronic acid. So the first step, bilirubin is added by added with a 1 glucuronic acid, and it becomes bilirubin monoglucuronide. And then it is added with another glucuronic acid, and it becomes bilirubin diglucuronide. This is called as a water soluble bilirubin. This is called as water soluble bilirubin. There are other names for this components, which is called as water insoluble bilirubin, is otherwise called as indirect bilirubin, And water soluble bilirubin is called as direct bilirubin. Or even better, there is another name. This is unconjugated bilirubin, and this is conjugated bilirubin. So water soluble bilirubin, conjugated bilirubin, direct bilirubin, all are the same. Water insoluble bilirubin, unconjugated bilirubin, and indirect bilirubin, all are same. Now, who is the molecule which converts a water insoluble bilirubin into a water soluble bilirubin? That molecule is glucuronic acid. Now, who is the fellow who does this conjugation? The enzyme name is CNS. Okay, sorry. The enzyme name is UDP glucuronyl transferase. UDP glucuronyl transferase. So it takes the help of a nucleoside called as UDP, uridine diphosphate, and along with that, it uses the UDP to transfer the glucuronic acid residue to the bilirubin, converting the what's insoluble bilirubin into a water soluble bilirubin, UDP glucuronyl transferase, and this is called as a conjugating enzyme. This is called as a conjugating enzyme. So the heme breaks down to biliverdin. See, there are 3 bile pigments. The bile pigments are the pigments which are present in the bile. Bile is a golden yellow fluid which is secreted from the liver. Okay, so the 3 bile pigments are biliverdin, bilirubin, and bilicyanin. Okay, so each one of them has a color. Biliverdin, bilirubin is yellowish in color. Okay, reddish yellow. Okay, then bilicyanin is a purplish color. Like that, biliverdin is a greenish color. So all of them have bile pigments, have colors. Okay, so the heme breaks down to give biliverdin. Biliverdin is reduced to bilirubin, which is unconjugated, and then it's conjugated by addition of 2 glucuronic acid residues, and next becomes a conjugated bilirubin. It becomes a conjugated bilirubin. So this is the process. So you have a bilirubin glucuronyl transferase here. Okay. So now, what will happen if this bilirubin levels increase? So you must know the normal bilirubin levels in our body. Normal bilirubin levels is 0.2 to 1.2 milligrams per deciliter. 0.2 to. What I'm speaking about is something called as total bilirubin. Now, this total bilirubin is made up of 2 things. You all know that: direct bilirubin plus indirect bilirubin. Direct bilirubin plus indirect bilirubin. Then what is the levels of direct bilirubin? Direct bilirubin is 0.2 to 0.4. Indirect bilirubin is 0.2 to 0.8. So it's always on the higher side, indirect bilirubin. Okay. So now what happens when the bilirubin levels exceeds? So when the bilirubin levels is greater than 3 mg per deciliter, we call that disease as jaundice. We call that disease as jaundice. And the bilirubin is yellow in colors, right? So there is an yellowish discoloration of the body, which is called as icterus. It is called as icterus. Yellowish discoloration called as icterus. So people tell, how do you find a person who is jaundiced? You look into his eyes. So why exactly is the yellow color of bilirubin reflected very aggressively in the eyes? That is because the eyes have a collagen called as type 1 collagen. Type 1 collagen. So it is something like this. Okay. So there's a lot of space. It's called as a long spaced fibrils, these collagens. So the bilirubin goes and lodges itself in this long spaced fibrils. So the bilirubin is taken up very well by the type 1 collagen, which is the most common collagen, which is the collagen which is present in the eyes. So basically that is the reason why the eyes are showing yellowish discoloration for you at a very earlier phase than the other types of skin or urine or something. There's an yellowish discoloration in the urine as well, but then the reason for the eyes showing is this. Okay. So now, this jaundice classification itself is an short note or an essay. So if you want to write, you will write like this. So jaundice can be classified into congenital jaundice or acquired jaundice. Congenital jaundice means it is present in the birth. Acquired jaundice means you are born, you do well, and then during the course of lifetime, you develop jaundice, that is called as acquired jaundice. Now, this congenital jaundice is again divided into two types: physiological jaundice, pathological jaundice. So, physiological jaundice is something, any jaundice that occurs in 2 days to 2 weeks time is physiological jaundice. The baby is born, first 2 days uneventual, no problem. From 2 days to 2 weeks, if jaundice is developing, it's called as physiological jaundice. Pathological jaundice is any jaundice present in less than 2 days or greater than 2 weeks. Very simple. The classification is very clear. So 2 days to 2 weeks, any jaundice, that is called as physiological jaundice. Physiological jaundice means the jaundice will settle down on its own. You don't have to worry. The jaundice will settle down on its own. But anything less than 2 days or anything greater than 2 weeks, the jaundice is going to come, then that jaundice is pathological. You need to worry about the jaundice because that's going to cause problems for the baby. Okay. Now this physiological jaundice is again divided into two types: breastfeeding jaundice, breast milk jaundice. See, what I'm trying to teach you here is going to be taught to you only in pediatrics and in general medicine. So basically, I'm trying to put up all the concepts from the final year into the first year so that you have a clear idea. Nobody's going to explain this to you in your final year because they're going to assume that you all know this. So I'm not passing this up. I'm trying to put it across to you so that you will understand better. So any jaundice that occurs in the first week. So I told you 2 days to 2 weeks, that is physiological jaundice. If it is occurring in the first week, it is breastfeeding jaundice. If it is occurring in the second week, it is breast milk jaundice. It's occurring in the second week, it is breast milk jaundice. So this is because of decreased breast milk output. So what basically breast milk does is, breast milk prevents the absorption of bilirubin from the liver, from the intestine to the liver. There is a circulation which is going on between the intestine and the liver called as enterohepatic circulation. So this enterohepatic circulation brings the bilirubin from the intestine to the liver. The breast milk cuts that off. So if the breast milk is not sufficient, then the absorption from the intestine to the liver is more. So this will cause jaundice. This is called as breastfeeding jaundice. So when the breast milk is very low, breastfeeding jaundice. When the breast milk secretion is very high, so much breast milk is given to the baby, then the breast milk has an enzyme called as glucuronidase. Glucuronidase. Now this glucuronidase will break down the glucuronic acid. So when the glucuronic acid is broken down, conjugation will not happen. That will lead to excess indirect bilirubin. So this is decreased conjugation. So look at how beautiful life is. The breast milk has to be secreted in exact adequate quantity. If you secrete less, breastfeeding jaundice. If the secretion is more, breast milk jaundice. So that is how the physiological jaundice is there. But then the body will adjust the breast milk. The baby will adjust the intake of the breast milk. That is the reason why this both this jaundice will resolve on its own. That is why they are called as physiological jaundice. Now we will come to pathological jaundice. In pathological jaundice, there are two classifications. The first classification is increased conjugated bilirubin. And the second classification is increased unconjugated bilirubin. Increased unconjugated bilirubin. So the conditions in which direct bilirubin or conjugated bilirubin is elevated are two. One is called as Dubin-Johnson syndrome. The other one is called as Rotor syndrome. The other one is called as Rotor syndrome. So what's the basic difference between the Dubin-Johnson syndrome and the Rotor syndrome is the Dubin-Johnson syndrome has a black liver. There is a black discoloration of the liver. Rotor syndrome does not have the black discoloration. Rotor syndrome does not have the black discoloration. Now, what are the jaundices with increased unconjugated bilirubin? Very interesting. So, when unconjugated bilirubin is increased, that means that the conjugation is decreased. So, basically, this is a decreased conjugation. So, who does the conjugation? The enzyme is UDP glucuronide transferase. You all know that UDP glucuronide transferase. So the first disorder is decreased enzyme quantity. Decreased enzyme quantity. The second disorder is enzyme quantity is normal, but function is defective. So in first disorder, enzyme is not present in adequate amounts. The second disorder, enzyme is there, but it is not working properly. So what are the diseases? Decreased enzyme quantity further divided into two types. Total absence of the enzyme, partial absence. Total absence, partial absence. If it is total absence, it's a very severe disease called as CNS type 1. If it is a partial disorder, CNS type 2. What is this CNS, sir? This CNS is called as Crigler-Najjar syndrome. Crigler-Najjar syndrome. So that disease in which the enzyme is not present in sufficient amounts is called as Crigler-Najjar syndrome. Type 1, complete absence of the disease. Type 2, partial absence of the disease. Which is the most severe among those two? Type 1 is the most severe among those two. And then the enzyme is present, but it is not working in properly. That kind of disease is called as Gilbert's syndrome. It's called as Gilbert's syndrome. It's called as Gilbert's syndrome. If you look at the page, you will get, wow, what is this? So much is there, but it's very easy. You only decide the jaundice is physiological or pathological. The baby is born, the jaundice is physiological, means 2 days to 2 weeks physiological. And in physiological, first week breastfeeding jaundice, second week breast milk jaundice. Pathological, you try and find out which fraction is elevated, conjugated or unconjugated. If conjugated is elevated, you just look for whether there is a black discoloration of the liver, then it's Dubin-Johnson. If it's not there, then it's Rotor. When it comes to unconjugated, there is no other option, but you must find out the levels of an enzyme called as UDP glucuronide transferase. If the level is normal, then it is Gilbert syndrome, because the levels are normal, but the functioning is not proper. But the levels itself is low, then you will find out how much low it is. If it's completely low, then type 1. Partially low, then it's type 2. Crigler-Najjar syndrome. So all this is about congenital jaundice. How do you classify Acquired jaundice, it's very easy. Acquired jaundice is classified as pre-hepatic, hepatic, or post-hepatic. That's all. It's based on the causes. Whether the cause is above the, outside the liver, whether the cause is inside the liver, or whether the cause is after the liver. That's all. Pre-hepatic, post-hepatic, hepatic, and post-hepatic. But before we jump into the various conditions that can cause acquired jaundice, we must know about the fate of bilirubin. So you all know that this is RBC that's breaking down to give heme, and this heme will give rise to biliverdin, which is giving rise to unconjugated bilirubin, which is conjugated in the liver. Where does the conjugation happens? The conjugation happens in the liver, and this conjugated bilirubin is secreted in the bile. So if you want to go for the anatomy, I can tell you that there is a right hepatic duct, there is a left hepatic duct. This is called as a common hepatic duct. So RHD, LHD, common hepatic duct. And this common hepatic duct joins with the cystic duct to give a common bile duct. Common bile duct. Okay, that's anatomy. This common bile duct opens into the second part of the duodenum, whatever it is. That's the basic anatomy there. But what exactly happens to the bilirubin? The bilirubin gets conjugated in the liver, conjugated bilirubin, then enters via the common bile duct and it goes into the intestine. So, heme is converted to indirect bilirubin. Indirect bilirubin is conjugated to direct bilirubin. Direct bilirubin goes to the intestine. In the intestine, the direct bilirubin is broken down by the intestinal bacteria into urobilinogen. Urobilinogen. Now, this urobilinogen has two fates. It can go to the kidneys and excreted in the urine. Okay, understood? It can go to the kidneys and it can get excreted in the urine. When it's atmospheric air exposed, then it becomes urobilin. Or it can give rise to another compound called as stercobilinogen. This stercobilinogen will enter into the feces. This stercobilinogen will enter into the feces. So the breaking down, conjugation, direct bilirubin entry into the intestine, in the intestine converted to urobilinogen, and if the urobilinogen is directly can be excreted in the urine, or it can go to be converted as stercobilinogen and go to the feces. Okay. So now, I told you about the jaundice. So that's very simple. Pre-hepatic, hepatic, post-hepatic. So the pre-hepatic means before the liver. So before the liver, the only causes of heme is RBCs. So any RBCs breaking down leads to hemolysis. And hemolysis leads to decreased RBC, which is called as anemia. So this is called as hemolytic anemia. So hemolytic anemia is the only cause of pre-hepatic jaundice. And since all the bilirubin that's coming out from the RBCs is indirect bilirubin, this is a increased indirect bilirubin or unconjugated bilirubin. This is an increased bilirubin or unconjugated bilirubin. Now this indirect bilirubin has to come into the liver. So there is some amount of otherwise no hemolysis. So let us assume that the body is not experiencing any kind of hemolysis. The indirect bilirubin is coming into the liver, and in the liver it has to be conjugated. So there is a lot of indirect bilirubin which is coming up, but then the conjugation process is not happening, or the conjugation process is decreased. Then what will happen? It's either decreased direct bilirubin or no direct bilirubin. So the conjugation process is absent means we will have increased IDB, indirect bilirubin, and sometimes increased DB or normal DB, direct bilirubin. So both the fractions are abnormal. Both indirect bilirubin and direct bilirubin are abnormal. Then it is called as hepatic jaundice. It occurs in the hepatocellular damage. It occurs in the hepatocellular damage. Now, what's with post-hepatic jaundice? So in a normal patient where the normal person where the unconjugated bilirubin is out and then it's also conjugated, it is entered into the liver. There is a lot of direct bilirubin in the liver and it has to go to the intestine. Am I right? But there is some problem. This direct bilirubin is not able to go to the intestine. So when there is no direct bilirubin coming into the intestine, there is no urobilinogen. Note this point because it's an MCQ. No urobilinogen formed. So basically, this urobilinogen has to come in the urine. Okay. But if the urobilinogen is absent in the urine, then it only means one thing, that is an obstructive jaundice. What are the causes of obstructive jaundice? The obstruction can be here, right hepatic duct. It can be here, left hepatic duct. It can be in the common hepatic duct. It can be in the cystic duct. It can be in the common bile duct. It can be anywhere. Bile duct atresia, cornal atresia. All those things can cause obstruction. Carcinoma of head of pancreas will press the pathway and cause obstruction. Okay, carcinoma duodenum can cause obstruction. A lot of causes can cause obstruction. So what will happen is this direct bilirubin will increase in the liver, then it will be entering into the bloodstream. It will be entering into the bloodstream via portal vein. And this portal vein will enter into the heart, from right heart to left heart, systemic circulation. This bilirubin will start appearing in urine. Bilirubin in urine, huge quantities. So if there is bilirubin in the urine and there is no urobilinogen in the urine, then that is perfectly a case of post-hepatic jaundice. And no urobilinogen means no stercobilinogen. So basically the urine will not have urobilinogen, no pale colored urine. Okay, it's called as a colorless urine. Okay, and the stool will not have stercobilinogen. That is also called as a colorless stools or a ash stools or pale colored stools. So anything like that sort, you must suspect obstructive jaundice. So the causes here, prehepatic jaundice, hemolysis. For hepatocellular damage, it can be viruses, it can be drugs, it can be alcohol, it can also be some congenital disorders, inflammation, neoplasm, trauma, all these things can cause hepatocellular damage. And about the post-hepatic, it's basically bile stones causing obstruction, carcinoma causing obstruction, or bile stricture. See, all the conditions that can cause obstruction to the flow of bile will lead to post-hepatic jaundice. Okay, now look at the table. If you look at the table, you'll see that bilirubin, urine bilirubin is present in hepatocellular and post-hepatic, whereas urine urobilinogen is absent. So there is no point. I mean, that is a very easy way of assessing a patient by just looking at his blood and urine. You can tell him whether it is pre-hepatic or post-hepatic or a hepatic jaundice. Okay, we do ERCP, we do MRCPs, we do a lot of complicated tests, ultrasound, abdomen, all things. But when it comes to the lab, we just ask for the serum levels and we just ask for the urine test. Okay, the urine urobilinogen is tested by the Watson-Schwarz test, and the serum bilirubin we just look and find out whether it is increased direct bilirubin and absent urobilinogen in the urine, then it's post-hepatic jaundice or obstructive jaundice. That's the only things you must look for. Okay, which fraction of bilirubin is increased in the blood. Okay, so this is all for adults presenting with jaundice. Okay, so you're not doing this for the babies. I'm telling you about acquired jaundice. When it happens in the babies, you classify that as physiological or pathological and deal with it. Okay, so now what is the treatment of jaundice? In adults, it is conservative. So if you see or ask your parents, go and ask your parents, they will tell you there's nothing. There's no treatment for jaundice. Some people use a drug called as Sleep-52. That's only hepatoprotective drug. They say that it's a hepatoprotective drug. It's not actually an allopathic drug. It's an Ayurvedic drug or homeopathic drug. So it's it does not resolve the problem. It's just helps the liver to recover. That's what is. But then the management is very conservative. As soon as the hepatitis infection subsides or as soon as the etiological factor is removed, then the jaundice subsides in adults. But when it comes to babies, that's a problem. The babies have to be treated. and the babies have to be treated so that the bilirubin levels should come less than 15 mg per deciliter before they are discharged. So somebody in your family is going to ask you, see, my baby is born, the baby is kept in a incubator because the baby is having jaundice. When are they going to discharge my kid? So that time you must be able to say that the bilirubin values must start to decrease serially. So morning bilirubin, when compared to evening bilirubin must be lesser. Night bilirubin must be lesser than the evening bilirubin. This is called as a serial decrease. So the bilirubin must increase serially. Number two, the bilirubin must come down below 15 mg per deciliter. So these are the conditions when the pediatricians will discharge the kid. Otherwise, they are going to hold the kid in the hospital. And when they are going to hold the kid in the hospital, they have two options. One option is called as the phototherapy. You might have seen grandmothers holding the babies in the sunlight. Okay, so what's the point here is the sunlight, it can break down bilirubin. So the bilirubin is accumulating in the body. The sunlight can break down the bilirubin, but then it's a very vague process. The sunlight contains a lot of colors, which are 7 colors, but there is only one color which can break down the bilirubin. That is a blue color light. So if you see in hospitals, they will be having a blue light that can break the bilirubin into water-soluble fractions. The other drug is phenobarbital or barbiturates. I told you that induces the heme synthesis. So that basically the heme will be formed and then the heme will go and inhibit the further heme synthesis. That's the idea there. So there are two options. You can either do phototherapy or you can do treatment with phenobarbital. Okay, so that is basically the treatment for jaundice. Okay, so now with that we have completed heme synthesis and metabolism. Now we are going to come to the structure function relationship. Okay, so always in all the workbooks you'll have the competency number mentioned. The competencies are specific skill sets which the Indian medical graduate must attain across the country. All the Indian medical graduates are expected to know compulsorily this competency. So the competency itself means this is a very important topic in your life which you must know. So I have mentioned the competency number in all the pages of our workbook. So this workbook is going to tell you all the important topics. What are the competencies are there? That's going to be mentioned here. So all of you know about the hemoglobin per se. There is another molecule called as myoglobin. So myoglobin and hemoglobin are basically same type of proteins, but then the hemoglobin is involved in oxygen transport, whereas the myoglobin is involved in oxygen storage. And where is the hemoglobin present? In RBCs, myoglobin is present in the muscles. And hemoglobin can bound to 4 oxygen molecules, whereas myoglobin can bind to only 1 oxygen molecule. And hemoglobin exhibits cooperative binding. Myoglobin does not have such cooperative because it's going to bind only 1 oxygen. It's not exhibiting any kind of cooperative binding. And hemoglobin has subunits, so it's quaternary structure, whereas myoglobin does not have subunits, so it is a primary structure. No quaternary structure, so it's a primary structure. So why do we have to learn about myoglobin and hemoglobin? That is because you must understand the following concepts. See, there is lungs which is loaded with oxygen, which means that there is something called as partial pressure of oxygen is very high, very high in the lungs. And then there is muscles, which is because of working, it is deprived of oxygen, which means the PO2 is very less. So there are 2 scenarios. One is happening in the lungs, the other one is happening in the muscles. So now we are speaking about something called as affinity. So affinity of the molecule towards oxygen. So hemoglobin affinity to oxygen increases as PO2 increases. So when there is more oxygen, then the affinity of hemoglobin to oxygen binding increases. That is exactly what cooperative binding is. So cooperative binding says that one oxygen binds, two will bind, two will bind, three will bind, three will bind, four will bind. So when the availability of oxygen is more, the oxygen affinity will be more for hemoglobin. But the myoglobin is not like that. Even at low PO2, very high affinity. So it will catch hold of oxygen, and store it. Okay, and store it. That's why myoglobin has very high affinity to oxygen than compared to hemoglobin. And affinity is directly proportional to something called as saturation. So more affinity means faster saturation. Okay, more affinity means faster saturation. With this backdrop, bring across a terminology called as P50. P50 means pressure at which the molecule is 50% saturated with oxygen. Now, if you see the things which I have written, the P50 hemoglobin will have increased binding only when the pressure of availability of oxygen is more. But myoglobin will take up the oxygen even when the partial pressure is very low, which means that the P50 of myoglobin is 8 mmHg, whereas the P50 of hemoglobin is 26 mmHg. So what does this signify? This signifies that 50% of myoglobin is loaded with oxygen at 8 mmHg itself, even at very less quantities of availability of oxygen, like say in the skeletal muscles, myoglobin picks up the oxygen. But mainly when the availability is 26, 50% of hemoglobin is filled with oxygen. So as the pressure increases, the affinity of oxygen binding increases in the hemoglobin. But myoglobin, even when the pressure is less, pressure is more, we don't bother. Here, the low pressure itself, myoglobin kicks off and picks up the oxygen. So this leads to a discussion on something called as a graphical representation of the picking up of oxygen by myoglobin and hemoglobin. This curve is called as ODC, or oxygen dissociation curve. The characteristics exhibited by myoglobin and hemoglobin puts the curves in two fractions. One is called as the myoglobin curve is called as a rectangular parabola or hyperbola. The hemoglobin curve, for that instance, anything which exhibits cooperative binding will present with the S-shaped curve or a sigmoidal curve. S-shaped curve or a sigmoidal curve. Now you look at the point at which the molecules are saturated with 50% of molecule is saturated with oxygen. This is for the myoglobin. So I'm going to write this here. This is 8 mmHg. And this is for the hemoglobin. It is 26 mmHg. So look at the curve of myoglobin. It takes off like a rocket and then it plateaus. But what about the hemoglobin? It slowly takes up, then it goes up, then binds, then it plateaus. So the hemoglobin binding oxygen is like this. Probably it binds one oxygen here, it binds the second oxygen here, binds the third oxygen here, and then the final oxygen here. So once the 4 oxygens are binds, it plateaus out like that. So this is called as oxygen dissociation curve, with the partial pressure of oxygen on the x-axis and saturation on the y-axis. So myoglobin is saturated at very low pressure. Hemoglobin is saturated at very high pressure. Now I am going to draw this like this. I'm going to draw this like this. Okay, this is saturation. This is PO2. Okay, so something which is 50% saturated, okay, 50% saturated, even at lower levels means it is increased affinity. So only when there is increased affinity, it can be saturated 50% at lower partial pressures. So when there is decreased affinity, a lot of pressure is needed to saturate 50%. So this is called as a left side and right side. So anything which increases affinity will push the curve to the left side. Anything which decreases affinity will need a lot of more oxygen, means it will push the curve to the right side. So you must understand that this is called as left shift and right shift. Left shift and right shift. So basically, left shift is factors increasing affinity, right shift is factors decreasing affinity. So what are the factors which are controlling the affinity? Before going into that, there is a magic molecule called as 2,3-BPG. This is called as 2,3-BPG, which is formed as a byproduct of glycolysis via a shunt called as Rappaport-Lubering shunt. Rappaport-Lubering shunt. So this 2,3-BPG has a very particular characteristics. Supposedly, these are the pyrrole rings, and oxygen is binding in the center. This 2,3-BPG will come. 2,3-BPG will come and kick that oxygen out. It will come and kick the oxygen out. So it will get lodged here and it will kick the oxygen. So 2,3-BPG is basically decreases the affinity of Hb to oxygen. It is always called as oxygen unloader. It is always called as oxygen unloader. You must understand that. Now, what are the factors which are decreasing the affinity? The factors which decrease the affinity are 2,3-BPG, oxygen will be unloaded, increased temperature, increased carbon dioxide, because carbon dioxide binds to Hb with 20 times more affinity, and carbon monoxide binds to Hb with 200 times affinity. 200 times per hour. So increased 2,3-BPG, increased temperature, increased carbon dioxide, all that decrease the affinity. The last point is tricky. In acidic pH, oxygen is unloaded. So acidic pH means pH is less. So I'm not gonna write pH less like this. What I'm gonna write is increased hydrogen ions. So when the concentration of hydrogen ions is increased, the pH is less. Why am I writing like this? Because I want the increase symbol to be always like this. So I want you to remember that easily. Increase 2,3-BPG, increase temperature, increase carbon dioxide, increase hydrogen ions. All this decrease the affinity of hemoglobin to oxygen, and the oxygen will be unloaded into the tissues. Now, homework for you, you will write the conditions of left shift. That's very easy. It's just the opposite of all these things. 4 conditions. You are going to write it on your own. So, yeah. So before going into that, I'm going to explain you about some things. See here. I'm going to draw the lungs here. I'm going to draw the lungs here. And then I'm going to draw the skeletal muscle here. Okay, I'm going to draw the skeletal muscle here. So the lungs is full of oxygen. I'm going to write lungs is full of oxygen. Okay, so now the blood vessels are flowing in. So Hb is here. This Hb binds with this oxygen the blood gets oxygenated, and this oxygen containing blood enters into the skeletal muscle. But what happens in the skeletal muscle? The skeletal muscle is doing work after work after work. So what happens is it utilizes the carbon dioxide and H2O. It gives rise to a component called as H2CO3 or carbonic acid, which again gives rise to a component called as H plus and HCO3 minus. H plus and HCO3 minus. So now the hemoglobin with oxygen has come into the skeletal muscle. But what do we have here? We have the H plus. H plus decreases the affinity of oxygen towards hemoglobin, and the oxygen is unloaded. Oxygen is unloaded. So basically the skeletal muscle also wants this. Skeletal muscle also wants the more and more oxygen. So now the HB after unloading oxygen is free. But I told you HB has a buffer action. So HB feels that this particular hydrogen ion, if it's accumulating in the tissues, it's gonna disturb the pH. So what happens is this H plus is bound by the HB. So now this is called as reduced hemoglobin because it takes up the H plus. This is called as the Bohr effect. pH mediated HB absorption of, HB O2 relation based on pH. Right like that. So the pH should not be squandered. So that is why the HB loses its oxygen and takes up the H plus. Now this H plus containing hemoglobin goes to the lungs. What happens is in the lungs there is so much oxygen, but when the oxygen availability is more, HB will drop the H plus there, and this HB will take up the oxygen again. Now what will this H plus do? It will bind with the HCO3 there, convert it into H2O plus CO2, and this CO2 will be expired by other lungs. So this process in which the HB H plus is dropped and HbO2 is taken up at high PO2 in lungs is called as Haldane effect. It's called as Haldane. So the Bohr effect happens in the skeletal muscles. Hemoglobin drops the oxygen and picks up the protons. And the Haldane effect happens in the lungs. Hemoglobin drops the H plus and picks up the oxygen. But in all this following process, there is one molecule, bicarbonate, which is in the muscle. But the bicarbonate is a basic substance. The muscle does not want to turn alkaline. So what it does is, it tells the bicarbonate, you go outside. But when the bicarbonate goes outside, it's a negatively charged molecule. It has to be replaced by some other molecule which is negatively charged, which is the chloride. So this effect is called as the chloride shift. Some people call this as hamburger phenomenon or chloride shift. So basically the three effects you must know are Bohr effect, HB picking up the protons in muscles to avoid pH changes, Haldane effect, HB dropping the protons and picking up oxygen at higher partial pressures at lungs, and then bicarbonate is exchanged for chloride in the skeletal muscle to maintain neutrality. That's called as chloride shift. So Bohr effect, Haldane effect, and chloride shift. Now I have taught you about the HbA. I have taught about the HbA2, HbF. Only one point. HbF is increased affinity to oxygen compared to HbA. That is one point. Point number two, HbF increased in a disease called as thalassemia. HbF increase in a disease called as thalassemia. You want the previous slide? Okay. 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 Now, what's HbA1c? Sugar binds to hemoglobin. That's called as HbA1c. When sugar binds to anything with enzymes, it is called as glycosylation. Without enzymes, it is called as glycation. Now, this is glycated hemoglobin. No enzyme, just glucose binds to hemoglobin. People don't understand the concepts. You have seen gulab jamun, right? Gulab jamun, you have the liquid there, jeera there, right? Outside. How much sweet is the jeera? That much sweet will be the gulab jamun, because the jeera seeps through the gulab jamun. Imagine like that. You have RBCs, you have the blood surrounding the RBCs. If there is more sugar in the blood, it will seep through the RBCs, it will enter into the hemoglobin and attaches to the hemoglobin. So more sugar in the blood, then more sweeter will be the RBCs, or more glucose will be there in the RBCs. Normally, less than 5% of the hemoglobin is glycated or has sugar. If it is greater than 6.5, it is diabetes mellitus. Greater than 6.5, it is diabetes mellitus. Methemoglobin, I have told you, Fe2 plus to Fe3 plus. If there is sulfur attached to Hb, again, no oxygen carrying. So basically, these two cause a condition called as cyanosis, or the bluish discoloration of the body, cyanosis. Again and again and again, they ask you one question in your examinations that is called as sickle cell anemia. So the basic pathology here is beta 6 position of hemoglobin, beta globin chain. There is an amino acid called as glutamate. It is replaced by another amino acid called as valine. Glutamate replaced by valine. Now, what will happen because of this replacement is two changes. One, glutamate is a negatively charged amino acid. Valine is neutral, which means basically the molecule loses negative charge. When it loses negative charge, it decreases the electrophoresis mobility. Decrease the electrophoresis mobility. This is with electrophoresis, MCQ. So it does not move like adult hemoglobin, rather it moves like a very slower fraction. What happens to the physiological property? The RBCs are normally ellipsoid in shape. Now, because of this mutation, they will be converted into a sickle shape. They will be converted into a sickle shape. RBCs will be usually going into the spleen and will be destroyed in the splenic capillaries. So there's no problem if they are discoidal shape or ellipsoid shape. But when they are becoming sickle shape, you must have seen a sickle. It is like this, right? The communist flags of Soviet Russia, China, all those, you have sickles. So this sickle clogs the splenic capillaries. So sickle basically clogs the spleen, leading to splenomegaly. And it will also lead to pain. At one stage, we don't have any other option other than remove the spleen, called as splenectomy, because this leads to a problem called as sickle cell crisis, where there's an acute occlusion, intolerable abdominal pain, and the patient is gonna collapse if you don't remove the spleen. So there's no other option. But what is the medical management? Is there any drug that can reduce sickling? There is a drug called as hydroxyurea, which can reduce sickling. RX means treatment. So we write, you will learn that in pharmacology. RX means treatment. All right. So these are also harmless substitutions. Okay. So HBC, HBD, HBE, all this are basically their other fractions, minor hemo, they are called as minor hemoglobin variants. So if you want, means you can see beta 6, beta 26, and beta 126. There will be changes, HBC, D, and E. Okay, but not so very important. I have also taught you about carbon dioxide binding to hemoglobin and carbon monoxide binding to hemoglobin. This is 20 times, this is 200 times, I told you. But this cherry red discoloration, if in your closed room without oxygen, like see in cars, many times you hear people are in the car, they try to put AC and all those things, then there was a lot of carbon monoxide accumulating. They died because carbon monoxide binds to hemoglobin, and hemoglobin cannot bind to oxygen. Their brain stops working. So many times we have seen forensic autopsies having people who are in the cars with their hands on the door levers. So they reached up to the door levers, but then they were not able to open the door because it is such incapacitating carbon monoxide binding to hemoglobin. Very terrible. That is a strong, that much strong affinity that is carbon monoxide to hemoglobin. Okay, so now all these problems so far, sickle cell hemoglobin, HbC, DE, carboxy hemoglobin, carbon hemoglobin, all these are qualitative problems. The quality of the hemoglobin is problematic. What if there is a quantitative problem? The quantitative defect is called as, the quantitative defect is called as thalassemias. The quantitative defect is called as thalassemias. So where is the quantitative defect? Decreased globin chains. Decreased globin chains. Okay. So now that can be divided into two types. Alpha chains or beta chains. So we need to know that the alpha chains are coded by 4 genes on chromosome 16. The beta is coded by 2 genes on chromosome 11. So what is basically happening here is there is some problem in the genes, so that's going to happen, lead to a disorder. Okay, so I'm going to write like this. If all the 4 genes are present, it is normal. All the 4 genes are present, it's normal. If 3 genes are present and 1 is absent, then it is called as silent carrier. If 2 genes are present and 2 are absent, then it is called as alpha thalassemia trait. If 1 is present, only 1 is present, then it is called as hemoglobin BART. I told you this. Hemoglobin BART is a hemoglobin that can move faster than the adult hemoglobin. If all the 4 genes are knocked out, the baby cannot survive. It will die in the uterus. That is called as hydrops fetalis. That is called as hydrops fetalis. So that's about alpha thalassemia. So decreased alpha chains, that is because of probably one or 2 or 3 or 4 of the genes are knocked off. So the alpha chains are not properly produced. It can be a silent carrier, it can be a alpha thalassemia trait, or it can be a HB BART, or it can be a hydrops fetalis. What about the beta chains? Now we know that the beta chains are 2 in number. So there may be conditions where one of the beta chain is normal and one of the beta chain is producing, if it's a plus symbol, it is less hemoglobin, less beta chain. If it is a 0 symbol, no globin. Okay. If it is a 0 symbol, then there is no globin. So one is normal, the other one is producing lesser change. This is called as thalassemia minor. This is called as thalassemia minor. The second condition is one of the genes is normal, the other one is not at all producing change, or both are producing decreased change. This is called as thalassemia minor. This is called as thalassemia minor. The last one, both are out. Both are out. Then this is called as thalassemia major. Thalassemia major. So in thalassemia minor, you don't have anything except minor anemia. No problem. Just minor anemia. Sorry, I think I have to. Thalassemia. This is thalassemia minor, thalassemia intermedia. It is thalassemia intermedia and thalassemia major. So thalassemia minor, thalassemia intermedia, and thalassemia major. So in minor, you have only minor anemia. In thalassemia intermediate, you have moderate anemia. And this will require blood transfusions. This will require blood transfusions. Whereas in thalassemia major, it will be very severe anemia. This will require lifelong extensive transfusions, and when that fails, they will need bone marrow transplant. When that fails, they will need bone marrow transplant. Thalassemia is also otherwise called as Cooley's anemia. Thalassemia is also called as Cooley's anemia. That's because of the bone lesions, because of the decreased production of globin chains. The time is spot on. I have finished at 9 p.m. So with this, the class is over, and I think Arun sir can take on from here. Thank you, sir. So any questions?
Bala?